Okay, so first thing first, tell me, what are the different, give me the names of some of the energies that you are aware of, the different types of energies. What are the different types of energies that you know of? Kinetic energy, good. What else? Potential, kinetic energy, potential energy. What else? If you've taken physics, then you know. Very good. Mechanical energy and electrical energy. Very good. And what else? I'm looking at the thermal energy. Very good. So heat and thermal, same. Next, physical is the potential energy. No, sorry. Thermal, nuclear energy. Very good. What else? You are able to listen to me. What kind of energy is that? You are able to listen to me. That listening, I can listen to you. What kind of energy is that? Sound. Very good. Sound. And you are able to see. You are able to see. Ooh, light. Very good. And heat, light, sound, mechanical, electrical. Then there is electromagnetic. Electromagnetic, that's responsible for the electromagnetic, that's responsible for our, like the TVs and like computers, all those things, right? And then comes the solar energy, right? The wind energy, right? And the atomic energy, okay? And then comes the chemical energy, right? Chemical. Okay, so and so forth. There are many, radiant is light. Light comes from the light. Okay, so all this is the chemical, and then there is these other types of energies like like gravitational pull, or the hydroelectrical, or geothermal, right? Those are more like a mixture of many other energies, but the big main ones are these. Okay, so these energies, how do you define an energy? How are you defining an energy? Define energy. A very broad one is the ability to do work. So this is the ability to do work. And work is not just us doing the work, like any type of work, moving, motion, some kind of motion. When you move from point A to point B, that's doing work. Right? So work is some kind of a transformation or change. And also there is the E is equal to mc squared. Then mass and energy can be converted. Mass can be converted to energy. You take coal, you burn it, it produces heat, and then it produces carbon dioxide, and then carbon dioxide vanishes. So that mass produced energy. So there is especially for us now, we are going to focus in chemistry in where is that in chemistry, we are going to focus on the chemical energy, and we're going to focus on the heat energy for us. Okay, and so here we see that, like we said, the ability to do work, or to bring about some kind of motion, or to produce a new substance, right? That's a chemical energy. So how the heat energy is used to break the bonds and then produce the new bonds. All that is like the use of the energy to produce something new, right? Everything there is energy present in everything. Even if something is sitting by itself, a book is lying on a table. What is that keeping that book on the table? That is the energy. That's a potential energy by virtue of which the book remains on the table. And then suddenly there is something happens, and there's a motion, and the book falls down from the table on the floor. right? So again, that is some energy, some mechanical energy came into play that transformed it, and its position changed from point A to point B. You know, although not a new substance is formed, it still remains a book, but the position has changed. So the motion has come into play. Okay. So all this is like some kind of a work is being done. Even to keep things stationary, work is being done. Okay. So you will study about that in the first law of thermodynamics in chemistry, but let's look at a simple ones for us in this course. Very simple ones. And that is, we are going to look at the second part is the energy and heat. Okay. And we're going to look at the units with regards to, as we said, our focus in this course is chemicals and the energy, you know, chemicals, chemical bonds, you know, break the bonds, how much energy is needed to break the bonds, and then how much energy is needed to make the bonds, and then any excess energy, where does it go? It goes into the air, those things. So we will look at the chemicals because, and then the heat. So what is this in this? What kind of? So here the energy, the unit, the SI, the standard unit for the energy is in joules. Okay, joules, Joules, and it's expressed as J. Okay, joule. And then there is also kilojoules, right? Kilojoules is 1,000 times more. So it's just a metric system. In the metric system, we see the joules and kilojoules are related, and there is a, you know, the difference of 1,000. So joules, one kilojoule is 1,000 joules. So how do you write down 1 kilojoule? 1 kilojoule is small k and large, like big J. Okay, so like that. So 1 joule. So what is the relationship between them? So 1 kilojoule is equal to 1,000 joules. Okay, so that's how you write. And what are the conversion factors? 1 kilojoule over 1,000 joules. Okay, or 1,000 joules over 1 kilojoules. So this is a very simple, you know, relationship in these units. Now, besides that, we also have another unit, which is called the calories. And it's a small calorie, CALORIES. And we write it as small c. So here this is a, so let me write this in red. This is a small c. Pay attention to that. Small or lowercase c. Lowercase c. Okay. So small calorie. Okay, calorie. And so what does it mean? Calorie means heat. Okay, so what is the relationship between calorie and joule? So the relationship is 1 small calorie, 1 calorie, one calorie, small calorie is equal to 4.184 joules. Okay, so again, so based on this equality, what are the conversion factors? Simple. The conversion factors are 1 small calorie over 4.184 joules, or 4.184 joules over 1 small calorie. All right. So these are the two conversion factors. Next is calories and kilocalories are also related. So what is that relationship? 1 kilocalorie. Same story. 1 kilocalorie. 1 kilocalorie is equal to 1,000 small calories. And what are the conversion factors? The conversion factors are same thing. 1 kcal over 1,000 calories, CAL, or 1,000 calories over 1 kcal. So these are the conversion factors from here. Okay, let me just make these small because I don't have enough space here. Okay, here is this thing. Okay. So we will be, so these are the relationships between these units, and you will be using them in this course as well as the, in the future courses for especially Chem 1A. Okay. So now make this nice and clear. All right. Now we are looking at the next situation where we are going to convert. Let's look at some of the conversions. Now this is again a part of your, so this is the conversion 1, 2, 3. All right, here we have the energy unit. So for example, you have, let's do some of these conversions here. Okay, so here is one conversions. Simple conversions are, okay, here. A person uses, so we are going to use this one, this problem 3.26, and this is on page 75. All right, here you have 750 kcal. A person uses 750 kilocalories on a long walk. Calculate the energy used for the walk in each of the following energy units. So we needed how many joules is that? How many joules is this? This is one piece. And then the second thing is how many kilojoules is this? Okay, kilojoules. So how many and how many? Okay, these. So how do you do this? So here, first of all, you're going to look at the relationship between kcal and joule. Is there a direct relationship? A direct relationship between kilocalories and joules based on what you see on the screen. Is there a direct relationship between kilocalories and joules? Sorry, kilocalories and joules, yeah. There's no direct relationship. There is a, between calories and joules, there is. But between the joules and the kilojoules, there is. But between calories and kilojoules, it is not. So we are going to write down what we know. So we know that we know there is a relationship. So this is going to be our strategy. Kilocalories have to first convert into calories. Okay, and then calories, sorry, this I always end up doing this wrong. So calories, small calories, and the small calories need to be converted into joules. And then later, that's what part we convert joules to kilojoules. Okay, so this is going to be our strategy because there's no direct conversion. So write down all that is known to you. So we know that 1 kilocalorie is equal to 1,000 calories, right? That's one piece. Next, we know that 1 calorie is equal to 4.184 joules. All right. And the next thing we know is that 1 kilojoule is equal to 1,000 joules. So these are basic, equalities we know. So based on that, you can write down the 2 conversion factors, although it is, kind of known, but I'm kind of like doing it again. The 2 conversion factors, 1,000 calories, 1,000 calories over 1 kcal. Next is 1 calorie over 4.184 joules, or 4.184 joules over 1 calories. 1 kilojoules over 1,000 joules, or 1,000 joules over 1 kilojoules. All right, so these are all the conversion factors from these equalities. All right, now, which ones are we going to use and which one are we not? So we're going to write on what is given to us. This is given to us, 750 kilocalories is given. So first is convert that to calories. So which conversion factors are you going to use? The first one or the second one? Kilocalories and calories. Which conversion factor? First one or the second one? Forgot, guys. Okay, here. Kilocalories. We want to convert from kilocalories to calories. We want the calories. So we are going to use this one, second one. Okay, very good. Now you are going to write down 750, sorry. Oh, every time there is an update, it is not necessary that it's going to be the best version. This one, this whatever they made in the Notability app on the top, it keeps interfering with, like, anyways. So here, 750 kilocalories times 1,000 calories. Actually, this should be a small c. Small c, okay? Small c. So pay attention to that and hold on to it. Small c, okay? Now, so that cancels out the kilocalories. Dimensional analysis, okay? So now you are left with this thing, 7, 5, 0, 0, 0, 0 calories. Okay, this is the first step. Next, we are going to convert. This is the first step. Second step is we are going to convert the calories, 7, 5, 0, 0, 0, 0 calories to joules. All right. So which conversion factor are we going to use? The first one or the second one? Calories and joules. First or second? Second. Very good. So here we see that we are going to use the second one because the second one is basically placing the joules in the numerator and the calories in the denominator. So we will write this here, 7, 5, 0, 0, 0, 0 calories multiply by joules. Joules is 4.184 joules over 1 calorie. Okay, now here you see that this calorie and this calorie cancels out and you are left with this big number. Now that's going to be a very big number. Let's see. 750 000 times 4.184. Okay, and that gives you, look at that. Look at that. This is just for fun we are doing now here. 3,138,000 joules. That's the number. All right. 3,138,000 joules. Next is 3. Next is you're going to take this 3,138,000 joules to so first is, this was the answer. So this is your answer number 1. So first answer, this is the answer to A. Okay, but next is the B, where we need to convert the joules. What is that? The joules to kilojoules. So kilojoules. How many kilojoules is this? So once again, what conversion factor will you use? First one or the second one? What conversion factor to convert joules to kilojoules? First one. Very good. So here we see the first one is this one, because kilojoules is in the denominator. Okay, guys? So here we see, let me make this small. Here, 3, 1, 138,000 joules times 1 kilojoule over 1000 joules. And you get here the joules, and joules cancel out. So 3 like million, 138,000 divide by 1000. And that gives you the kilojoules is 3,138 kilojoules. And that is the answer to B. All right, guys. So it's kind of like, a good practice for the dimensional analysis also. So we covered here the conversion. So you have to look at, is there a direct conversion or not? If there is a direct conversion, go ahead and simply set up the conversion factors and then go from there. If it's an indirect conversion, then you have to follow the steps. So all the things that are given to you. Now, certain things may be missing from your handout. Feel free to write these conversion factors, the ones I'm showing you on the screen right here. So please feel free to write down all these conversion factors and the equalities. So these may be missing from the tables in the handout, but that's one piece. All right. Next is we are looking at this is the common energy, right? The common heat that comes from breaking the bonds, making the bonds, the amount of energy that is needed to start a reaction, the amount of energy that is released when a reaction occurs, exothermic, endothermic reactions and so forth. Okay, so just hold on. Yes, one of the students raised their hands. You have a question?
Yes, Professor. So do we have to put the answer in the lowest significant figures for all of this?
Yeah, see, significant figures in this case, it doesn't apply. Although significant figures should be used every time, like whenever there is like whenever you're doing some kind of measurements, right? Measurements, of course, in these reactions, in these type of experiments also, we do measurements. We use thermometers and other devices. So, but the thing is, see how many exact numbers there are. We see these exact numbers are, look at all the exact numbers here. 1 calorie, 1000 calories, and then 1000. The only thing is the 4.184. Anytime there is a decimal involved, so we use that. Now, even if you look at the decimal piece, we have like 1, 2, 3, 4. We have 4 significant figures. So if here you see, you are getting 4 significant figures. Throughout this process, all this can be done in one line. All these reactions all these conversions can be done in one line, in one row. But let's see if I can do this, set this one up for you. So in one row, let's do this here. 7. Okay, 750 kcal. Okay, if you were to set this up in one row, times, now we have 1000 calories over 1 kcal times, now we need to get rid of the calories, right? So 4.184 joules over 1 cal. Okay, so in this case, we got the answer 3.138,000 joules, if the answer is in joules. Now, obviously, here, yes, if you have significant figures that only apply here, the others are all exact numbers. So we should have technically 4 significant figures, but this is a big number. So you will have to transfer it into a scientific notation in order to make this. You cannot just drop the numbers. So this is the standard notation. And in order to make the answer in 4 significant figures, you will have to move the decimal. So move the decimal 1, 2, 3, 4, 5, 6, and you stop. Okay, so in this case, then the answer becomes here 3.138, 4 significant figures, times, you moved it 6 places, so raised to the power 6 joules. So in that case, yes, it is giving you the answer as 4 significant figure, not in the standard notation. Standard notation, it's not possible. Just don't drop those 3 zeros, because that's going to change the value of the number. So in the standard form, the answer in 4 significant figures is not possible, but in scientific form, yes. And in scientific form, because you need those 4 significant figures, so all those places after the decimal are needed to make it into a 4 significant figure. Okay. So this is one thing. Now let's look at the other one. If we move to the next one, and the next one was again here, 750 kcal into 1000 calories, right, over 1 kcal times 4.184 joules over 1 calorie times, now because the answer is in kilojoules, so 1 kilojoules over 1000 joules. So here again, there's only one this piece right here. The others are all ignored. So 4 significant figures, and you see even in one line, these are cancelled. Kcal, 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 kcal. Calories, calories, calories. Joules and joules cancel out, and you're just left the answer in kilojoules. So in order to make this whole thing, what did we get here? We got 3. So this is already giving you 3.138. So this already is 4 significant figure. You don't need to convert this into scientific notation. So this answer is 4 significant already. Okay, and this is the kilojoules, sorry. Always write the units. You get that?
Yes.
Okay, yeah. So always, that's a good question. So here, this is this 4 significant figures in this case.
So the answer for number 2 would be, by right, would be 3.138 times 10 to the power of 6, right?
Yeah.
For
Yeah,
number 2.
that is the, yeah, if the, the choice is given to you based on the, if in the multiple choice, if you have this answer, this is actually more exact. Like, I mean, because we're looking at 4 significant figures here and the rest of them are anyway 0, so we are dropping them. But, every time the decimal comes into play, a little bit of the error also comes into play. That's the thing, right? So it depends if you're doing a calculation based on, where is the undo now? See, that's the thing. Yeah, so every time there is what I mean to say is that every time look at the choices first of all. If the choice is between the significant figures and the question is specifically asking you, find a significant answer to the correct number of significant figures, then yes, you go by that you, even if you have to convert the question into scientific notation, the answer into scientific notation, you go with that method. Okay, otherwise just choose whatever choice given in the multiple choice. All right, so next we are doing, after the conversions, we are now looking at the nutritions. Okay, so this is all this, for Chem 1A, I know this is maybe a little bit heavy stuff, but you should know all this, because all this you're definitely going to need in your next level course. Chem 1A, Chem 210, any of the courses you're taking, Chem 25, any course, a higher level college chemistry course, okay? You would need that. We do a separate unit on thermochemistry, okay? Next we are looking at the situation with nutrition. Now, in nutrition, we use the calorie, but it is the one with the capital C, okay? Capital C, okay? A lowercase, uppercase C, or it's also called uppercase C, uppercase C. Now, this uppercase C for calories. This is also called the nutritional calories. Nutritional calories. Now, this is something you see on the labels, on the food labels. Okay. Now, because your body has like a different type of setup for, because the thermochemical reactions, biochemical reactions, there is a difference between a chemical reaction occurring inside a test tube versus a chemical reaction occurring inside a body. In a test tube, you can add as much as chemicals you want, or in the beakers, or in an Erlenmeyer flask in a lab. But in your body, there is always a certain threshold. So there's only always a little bit, teeny amount can produce a large amount of energy also. So here's something, note down this. One big calorie, the nutritional calorie, CAL. Okay, that's with capital C. Okay, one big calorie with a C calorie is equal to 1 kilocalories. So what does this mean? It means 1,000 small calorie make one big nutritional calorie. So the focus is here. Pay attention to this piece here. This C and this C. Okay, so that's a main difference. And with that said, the other unit is 1 big calorie, the nutritional calorie, is equal to 4.184 joules. Remember, there's a difference here now. 4.184 kilojoules, sorry, kilojoules. 4.184 kilojoules. And what does that mean? This means 4,184 joules. So these are the conversion factors. Okay. Now, how do they do this? They do this in an insulating flask. Those are called the calorimeters. Now, you don't have to worry too much here if you don't, get that. But calorimeters are just like, you have like coffee cups. Okay. Coffee cup is a kind of calorimeter, not the best kind, but it is still a coffee cup. A coffee cup acts like a calorimeter because it traps the heat. So it has some insulation. So it traps the heat and it provides some kind of insulation. Insulation means the heat cannot escape for some time. It's only temporary because these coffee cups also get hot. So some insulation is provided. Insulation means that, in cup, so the heat cannot escape. Now, if we want to measure how much of the heat is being released in a chemical reaction, or how much heat is being absorbed by a certain substance, or how much of the heat is being released by a certain substance, we do these type of reactions in a substance called calorimeter, which looks like a calorimeter is like a coffee cup, right? And if you seal the coffee cup, then all the heat stays inside if you cover it. Okay, so that's the way we do it. Now, energy values. Now, there are energy values, like in the apple, there is some carbohydrates, fat, protein. There's no fat, there's no protein. If you note, if you read this label somewhere, the apples, the 15 grams of carbohydrate is present. Okay, so in the food, if 1 gram, so this is how they put this in food. Let me put this here in the food. Okay, here the energy values for the food are the kilocalories or kilojoules. So kilocalories or kilojoules. This is something you must have seen in the labels, and these are obtained from burning 1 gram of whatever, 1 gram of carbohydrate, fat, or protein, whatever is there. So kilocalories per gram. So in the food, it's kilocalories per gram. How much of the heat is being released? So let us say, for example, you have apple. So apple, the main source, the main thing is carbohydrates. I'm going to just put it here. CHO stands for carbohydrates. Carbohydrate. Okay, so we know there are carbohydrates, fats, proteins. So in apple, if you have 15 grams, in apple, there are 15 grams of carbohydrates are present in an apple, and those are releasing 60 kilocalories of heat. Okay, the energy that you're going to get, 60 kcal, small calorie, okay, and that is equal to 260 kilojoules of heat. Okay, let's look at something else. Let's look at something more. Beef or potatoes, for example, potato. Potato also has a lot of carbohydrates. To change this, make it something else, less carbohydrate. Okay, let's do this. Salmon, okay, fish, salmon. Okay, so what does the salmon have? The from carbohydrates, there the amount of carbohydrates present in salmon is 0 grams. What else is present in fat? Fat present in a salmon is about 5 grams. If the salmon is 3 ounces of salmon, 3 ounces of salmon contains 5 grams of fat. And the 3 ounces of salmon also contains proteins. And how many proteins are there? Proteins are 16 grams of protein present in 3 ounces. 3 ounces, not 0 ounces, sorry, 3 ounces. Okay, so that's the 3 ounce of salmon can give you, are all these things are present in a salmon. So total energy you get from salmon is 110 kilocalories. And this also is equal to 460 kilojoules. So this information and much more similar information is found in the food labels, right? Now let's do this problem here. It's a very interesting problem. It's a study check problem. Study check problem. And the study check problem is on page 78. And the problem is 3.6. Study check 3.6. Okay. Here, using the nutrition values of 1 serving of crackers. So you are given crackers and you're given some value for the crackers. So let me write those down for the crackers. What are, so this is again on the food label or table. So serving size, there are 14 crackers, and these 14 crackers weigh 31 grams. Okay. Serving size per container, about per container, about 7. I don't know what that means. So this is total calories. Total calories given is total calories that you would get from serving size per container. Seven crackers. So serving size so I don't know, it's a 7, I don't know. Anyways, so amounts per serving. So there are total calories of 130. Okay. And in calories from fat. So total calories, 130 calories from fat given is 40 kilojoules from fat. I don't get it. It's not very clear. I don't know if it is this one or which one. Hold on just a minute. Oh, wait, I was reading. Okay, I was reading the wrong thing. I'm sorry. Okay, here. So anyways, these are the, so it is that. I was reading the wrong stuff. The more clear stuff is here. They have extracted it in the table 3.7. So this is what we will refer to. Table 3.7. Okay, so typical energy food value of the three food types. So carbohydrates, carbohydrates, 4 kilocalories come out per gram from 1 gram. And in kilojoules, it is 17 kilojoules per gram. All right. Then you have fat. Fat is 9 kilocalories per gram. So 1 gram will release, 1 gram of fat will release 9 kilocalories of heat, or 38 kilojoules per gram. And then protein. Protein, 4 kcal per gram, 17 kilojoules per gram. Okay, this is all given to you on the table. All right. So this is the information we have, and this is all, and also coming from the, from the, this is, they have extracted it in this table. Okay, now comes a question. Using the nutrition values of 1 serving of crackers in sample problem 3.6, the same thing, calculate the energy in kilojoules. Okay, so these are the values of energy values in kilojoules for each food type, around kilojoules for each food type to 1/10th place. Okay, and then what is the total energy? So we will see this, we have to convert this to kilojoules. Okay, so we are given so this actually question relates to the problem. 1 serving contains, so here 1 serving, so this is something that you have to relate to, refer to problem 3.6, which is already solved. So this is in continuation to that. So here's some more information we need. We are given 19 grams of fat, 19 grams of fat. We are given 19 grams of carbohydrate, 4 grams of fat, 19 grams of carbohydrate, 4 grams of fat, and we are also given 2 grams of protein, 2 grams of protein. Okay, so this is given in the solved problem. So this question is in continuation of that. Okay, what is the energy of each of the food type in kilojoules per gram? Okay, now what you will do, very simple, you are going to now put for the carbohydrates. So we are given 19 grams of carbohydrates. Multiply by what is the actual value of 1 carbohydrate. Remember, per means 1 gram. So this 1 gram, this means 1 gram. Per, this means 1 gram. This means 1 gram. So 1 gram of carbohydrate gives you 17 kilojoules of heat. So 19 grams is going to give you how much? Okay, so this is how you will set it up. Similarly, let's look at the fat. 9 kilocalories of 9 kilocalories of fat times what is given? You are given 38 kilojoules of fat coming from 1 gram of fat. Okay, so then whatever you get here, you write that. And then the next is the proteins. Proteins, you have 2 grams of, why am I writing that? 9 grams of fat. Okay, 2 grams of protein times 17 kilojoules over 1 gram of protein. So this is how you will set up the problem. So if you see here, grams of carbohydrate cancel out. Grams of fat and grams of fat cancel out. Grams of protein and grams of protein cancel out. And you're just left with the units of kilojoules. So now let's do this math. Here, 19 times 17, and you have 323 kilojoules. The other one is 9 times 38, and you have 342 kilojoules. Next is you have 2 times 17, and you will have 34 kilojoules. Okay, so this is coming from carbohydrate, fat, and protein, individual. Okay, individual. So this is how they do. They look at the food content, right? They look at the food. And in the food, they identify how many grams of carbohydrate is present, how many grams of fat is present, how many grams of protein is present. Okay, so once they get all these information, then they know that through, the calorimetry and those things, they find out that 1 gram of carbohydrate releases some amount of energy, 1 gram of fat releases some amount of energy, and 1 gram of protein releases some amount of energy. So then they set up the problems the way I have shown, and they get the individual. Okay, so we see here that the carbohydrate is 323, fat is 1, maybe I made a mistake, 9 times 38. And 19 times 17. And proteins are 17 times 2 is 34. Okay, so I see that in your book, it's 150 kilojoules for the fat. Fat is 150, 9 and 38. Yeah, I don't know. So there seems to be a discrepancy in the answer. Okay, in the book. In the book with regard to the fat. The book is saying it's 150. The other one is 320, and this 323, it's okay. This one was 34. This is in the book is giving 30. So this is also, kilojoules. Okay, but this one from the book is, the answer is different. Okay, so anyways, we have, now if you add all this, now they're saying what is the total? So this should be, oh, I know what the problem is. Okay. No, we are fine. This is the discrepancy here. The question is 4 grams of fat and not 9. Yeah. So we are fine. I mean, if we let's just change, it doesn't matter. So it's if you use the 9 grams of fat, then you get this. Okay. So that's the discrepancy here. Your book is using 4. Okay. So here you take then 323 plus 342 plus 34, and you're going to get 699 total, 699 kilojoules of heat or energy, right? So this is how they calculate on the energy bar. So this is all interesting, biochemistry. Okay, very interesting. Biochemistry is really very interesting, but this is what they do. Okay, next let's look at the problem with the next part is the specific heat. Okay, next, specific heat. Now, every substance has a capacity to heat. Every substance has a capacity to absorb heat, some amount of absorbing. And the amount of heat that is absorbed, the same amount of heat is released. So every substance has some capability to, absorb some amount of heat. Now, what is specific? Specific heat is defined as the amount of heat needed to raise the temperature of exactly 1 gram of substance by 1 degree Celsius. Okay, so this thing, specific heat, SH, is equal to M times C times delta T. Okay, now what is M? M is the M is the mass in grams. Mass in grams. C is the heat capacity. Okay, heat capacity. How much can an object absorb the heat? Not everything absorbs heat at the same time, at the same, amount, in the same, way. Water takes very long to heat, but sand gets heated up quickly. Water takes very long to cool down. It releases heat also very slowly. And the sand releases heat quickly also. So sand cools down quickly. So the heat capacity is C. And delta T is the change in temperature before and after. Change in temperature before and after. Change in temperature is delta T. Is T final temperature minus the T initial temperature. So whatever the initial temperature and the final temperature was, that difference in the is called the delta T value. Okay, and this is generally in degrees Celsius. Okay, so that's how we do. So specific heat, the units for specific heat become, units are calories. So for example, everything is it's very specific. So it's units in calories per gram degree Celsius. So you see, using the unit, you can write a definition of specific heat: amount of heat that is absorbed by 1 gram of substance to bring a change in temperature by 1 degree Celsius. So you see, per gram and per degree Celsius is 1 gram. By 1 degree Celsius is the specific heat. Now, the same thing can also be written in joules. So joules per gram degree Celsius. Remember, calories and joules can be converted. Now, let's look at for water. What is the value for water? In calories, it is 1.0 calories per gram degree Celsius. That's the value for water. And joules, the value for water is 1.84 joules per gram degree Celsius. Okay, so there are, there are actually, it's not, yeah, one second. I wrote the wrong formula. One second, guys. This is the amount of heat, Q. This is the amount of heat. I made a mistake here. Sorry about that. So this is Q. And Q is the amount of heat released or absorbed. Heat capacity is the specific heat capacity. And this is not C, your book is using an SH, specific heat. Okay, so Q is the total amount of heat absorbed or gained. Okay, either absorbed or released. Okay, so the heat value, if it is released, it can be negative. If it is absorbed, it will be positive. Okay, so the number negative is just a flow of heat. Now, Q is that amount of heat that is exchanged in a reaction, or even like substances, like they can absorb heat or release heat, and that depends on their capacity to absorb heat. And 1 gram relates to the specific heat capacity. Okay, so anyways, for the water, we have these values. Now, calculating the heat loss, let's do that. Okay, let's do this problem. So here we have Q. So this is a study check problem. 81, and the problem is 3.7. 3.7. Okay, so write down what all things are given to you. How many kilocalories? The question is kilocalories. How many kilocalories are lost when 560? So the mass given is 560 grams of water. Always very specific to, the substances. Water, it cools from, so the T initial temperature is 67 degrees Celsius, and its final temperature final is 22 degrees Celsius. So how many kilocalories of heat, how many are lost? So always write down the formula. So here we have Q is equal to M, SH or C and delta T. Okay, so here we are talking about water. So the specific heat of water in terms of calories is 1.00 calories per gram degree Celsius. Okay, calories per gram degree Celsius. That's the specific heat for water. This is the water. Okay, now delta T you will have to find. Delta T is T final minus T initial. T final is 22 degrees Celsius minus 67 degrees Celsius. So you're going from a final like 67, a lower, to a higher. So here you have 22 minus 67, and that gives you negative 45, which is fine. The sign is always going to be of a big number. So it is lowered. Temperature is lowered. The heat is given off. Okay. Now, so this value is known. This is known. We calculated delta T. We have the mass. So just put so Q is what we are trying to find. Okay, we are trying to find Q. So, okay. So here we have Q is equal to M times S times delta T, SH, specific. So, in some other books, it's also written as C. I'm not used to writing SH, but it's also written as C. Okay, delta T. Okay, and delta T is also, so I'm MC theta. Theta is like delta T. Okay, so this is the same formula. Okay, anyways, so M is 560 grams times 1.0 calories per 1 gram degree Celsius times negative 45 degrees Celsius. Okay, so here you see the grams and grams cancel out. Degree Celsius cancel out. And you're just left with the unit of calories. So negative 45 times negative 45 times times 560, and you get negative 25,200 calories. Remember, but the question is asking big calorie. The question is asking for the kilocalories. So we will have to convert. So Q is equal to negative 25,200 calories times 1 kilocalorie over 1,000 calories. And here you see that calories and calories cancel out. And then, so this is 1,000. Okay, so 2,5,200, sorry, 2,5,200. 2,5,200. Divide that by 1,000. And you get 25, negative 25.2 kcal. And this is the negative sign, only means that the heat is being released. So here, negative sign relates to release of heat. It makes sense. Look at that. The initial temperature is high, the final temperature is lower. So where is the rest of the heat given? To the surroundings. So released to the surroundings. That is why when you touch an object, it feels hot, because the object is really giving away heat. Okay, so that's one piece. All right, next is the change of state. Now, change of state is, next is 6. So hold on to your questions. We will, we have to finish this. So change of state. Now, this you see very all the time, change of state. So you see, anytime you have a solid, you can convert the solid to a gas, and you can convert the gas to a liquid, and you can similarly convert a liquid to a solid, and all that, So let's do this first. Okay, so solid to a liquid, what is that called? When you let's take a liquid to a solid. What is that called? Liquid to a solid. Let's say water, convert to a ice. If you have water, ice, this becomes ice, and this becomes water vapor or steam. Okay, so this is the vapors of water, or it's also called a steam, wet water. Okay, so now tell me. So this is the water. What is it called? Water becoming solid? Freezing, right? So this process is called freezing. So this is freezing, Freezing. And freezing occurs always when the temperature goes down. So temperature goes down, freezing occurs, right? Gas to a liquid. When does that happen? Gas to a liquid. What is it called? Water vapors in the air converting to liquid. What is that process called? All these are test questions, guys. Condensation, very good. So this is condensation, and condensation also occurs when the temperature goes down, when it's cold, right? When it touches cold water, only then it happens. So the temperature is down, right? Now, solid to a gas. Do you guys know that? Solid to a gas? Converting directly. No, not evaporation. This is called sublimation. Sublimation. And this occurs when the temperature goes up. When you take a solid, you heat it. You take a solid, you heat it. It can directly convert, or when the temperature is increased, even if you're not heating, sometimes with a little variation in the temperature increases, a solid can convert to a gas. It can evaporate. An example of that is iodine. Iodine is solid at room temperature. Slight variation in temperature, it vaporizes. Okay. Another example is like dry ice. Dry ice is carbon dioxide, solid carbon dioxide. So very cold, but it becomes a solid carbon dioxide. The moment you leave it in the, on the room temperature, and it evaporates into carbon dioxide. Okay, gaseous carbon dioxide. So that's one piece. Next is, let's look at the other one. Liquid to a gas. How does that happen? How do you convert a liquid to a gas? Liquid to a gas is through boiling. And as you're saying, evaporation also, when there is a slight increase in temperature. Okay, so here you see the temperature is increasing. All right, next is gas to a solid. How can you make gas to a solid? gas to a solid. This is called solidification and occurs when the temperatures are down, very cold temperatures. So this is solidification when the ice, is seen on the surface of the glass. So it happens in extremely cold weather when the, very freezing cold air, which already has the water loaded with water vapors, it strikes the cold glass surface. It immediately forms like those beautiful icicles or some kind of like snowflakes, those things. Okay, so beautiful patterns you will see. So that's solidification. Next is solid to a liquid. When does it go from solid to a liquid? Solid to a liquid. Melting, right? So this is melting. So all these you should know, and that happens when the temperature is increased. Okay, whenever you heat some solid little bit, it begins to melt. Like butter at room temperature, it will melt, but in the fridge, it will remain as a solid brick. So these are the things. Now here's pay attention to this. Now here you will see the temperature, one side, when a liquid is going to solid, it is cold, the temperature is going up. But on the opposite side, where the solid is becoming a liquid again, the temperature has increased, right? Now, on the other hand, when you see the temperature falls down, when the temperature is lowered, solidification happens. But when the temperature is increased, the sublimation happens. Same story. One side, the temperature going down, the other side, temperature going up. You see that? So that's one thing where there is but there's a same amount of temperature. One going up, when the amount of the temperature is what? It shows you the amount of heat, right? So the same amount of heat is released when it gets converted from a solid to a liquid and then liquid to a solid. The amount of heat is the same. The only difference is releasing and absorbing. So when it's releasing, it's releasing like a solid releases the heat, so the temperature rises. But the freezing is, where the liquid, the temperature goes down, and then it kind of like at a lower temperature, the freezing will occur. But at a higher temperature, the melting will. But the amount of heat that is exchanged is the same. Now, what is the name of that heat? One is the heat of fusion, and the other is the heat of vaporization. So here, the heat of fusion, and the heat of vaporization. So these are the names of the heats that are involved in bringing the transformation from like a solid to a liquid, or from a liquid to a gaseous state. So evaporation, let me write this down, evaporation. Okay, the heat of fusion. What is that? It is the amount of energy, amount of heat added to convert exactly. So let me write this down. Heat needed to convert 1 gram of solid to liquid, right? That's the amount of heat that is needed to convert 1 gram of solid to a liquid. And what is the heat of vaporization? The heat of vaporization is, or the evaporation is the same. The heat of vaporization is exactly the same. The heat of vaporization is the heat needed to convert 1 gram of liquid to gas, to its gaseous state, right? The state is this, the material is the same, like the 1 gram of liquid to gas. Okay, so that's the heat of fusion and the heat of vaporization. So what are the units? The units are kilocalories per gram or joules per gram. Okay, the kilocalories, the heat of fusion is kilocalories, calories per gram or joules per gram. So these are the units. And the heat of vaporization, the same story, calories per gram and per gram means 1 gram and joules per gram. Okay, so and then you can put kilojoules per gram and those things can be changed. All right, now let's look at the some of these problems. Okay, so let's look at the study check problem. Study check. Okay, and this is 3.8. And this is on page 83. Okay, here in a freezer, 150 grams of water. 150 grams of water. Okay. Of water at 0 degrees Celsius, 0 degrees Celsius is placed in the ice cube tray. Okay. How much heat? So we need to find how much heat, right? How much heat? And the question is in kilocalories. How much heat in kilocalories must be removed to form ice cubes at 0 degrees Celsius? So in this case, you need the value of the heat of fusion. Okay, substances have these values for the heat of fusion. Now let me write down here the values for the heat of fusion for water, and that's going to be given to you. Okay, so you will be given the heat of fusion. Now in this question, they have not obviously stated it. The heat of fusion. For water. Okay. What is that? The heat of fusion for water is heat of fusion for water. Every substance has different. For water given is 334 joules per 1 gram of water. Okay, this is given. Okay, yeah, 334 for water. Water, this is given. So all you need to do is write down here 150 grams, or actually this is known, not even given. This is known, and that will be obviously provided to you, but this is known value. It is known that the heat of fusion for water is okay, so 150 grams of water multiply by, now remember this thing, you can write down the conversion factors. 334 joules per 1 gram, or 1 gram of water obviously is 334 joules. These are the two conversion factors, and we need to use that conversion factor that first converts 150 grams to joules. So we are going to write down here 334 joules over 1 gram. Okay, and then the next we can continue here because the question is asking us in kilocalories, right? So we know that joules, what is the relationship between joules and calories? Joules and calories? Okay, I think this is, okay, let me put this here. This might be a little confusing here. Okay, 150 grams of water is given, and you need to find the kilocalories. So remember that there's no direct conversion between grams to kilocalories. So what will we do? We are going to first convert grams to joules, because we know the heat of fusion given, the heat of fusion. The heat of fusion becomes our conversion factor. Okay, the heat of fusion converts the grams to, to joules. So convert grams to joules, and then these joules then have to be converted to calories. Okay, so that relationship is already known. One second, where is that? 1 calorie is that is here, joules. 1 calorie is 1 calorie is one. That's a nutritional calorie right here, all the way here. 1 calorie is 4.184 joules. So no, yeah. So that's going to convert the joules to calories, and then calories to kilocalories. I'm so sorry. Hold on. Just a minute. Let me set this up problem in a more like a linear fashion. So hold on. Okay, so I was going by a very long route. So here is, this is a more direct route. This is known. This is the heat of fusion of water in calories. And because the question is asking us how many kilocalories are there, you can just do this, use this information rather than the joules. Okay, so 1 kilocalorie is 1000 calories. So based on this, there are two conversion factors, and those are 80 calories over 1 gram of water, or 1 gram of water over 80 calories. The other one is 1 kcal over 1000 calories, or 1000 calories over 1 kilocalories. All right, so these are all known now, and the two conversion factors. So these are the conversion factors from the known equalities. Okay, so you create those. Now, what is the strategy you're going to form? The strategy is, we are going to take the grams, convert them first into calories. Okay, and then this calories are then converted into kilocalories. Okay, this is a simpler method. All right, now here, the grams to kilocalories, you're going to use the heat of fusion, and that's going to convert into the calories. Here, you're going to use the, the conversion factor to convert the kilocalories to calories. So that's one of this. So this is also called the delta H. This is also called the heat of fusion, HFUS. We write it like that. Okay. Anyway, so now we have 150 grams of water, 150 grams of water times, okay, convert to calories. So 80 calories is produced when 1 gram of water, or 80 calories is involved in transforming 1 gram of, ice to a liquid. Next is, from here only you can start this, 1 kilocalorie over 1000 calories. Okay, so here you see the grams and grams cancel out, calories and calories cancel out. So just multiply this. This is a simple 150 times 80 divided by 1000. 150 times 80 times 1 divided by 1 times 1000. What do you get here? Well, K cal. Okay, got it, everyone? We just have to finish this now. Just a little bit more is left. So 12 K cal. All right. So next is the same is the case for the heat of vaporization. Now, the same thing. Let's do the study check problem for that one. The study check. '86. And page 86 page number. And the problem is 3.9. 3.9. Okay. Now, in 3.9, 3.9. Okay, here you are given when a steam from a pan boiling water reaches cool window, it condenses. How much heat in kilojoules? Heat in kilojoules, okay, is released when 25 grams, 25.0 grams, okay, of steam condenses at 100 degrees Celsius. The temperature given is 100 degrees Celsius. So here, that's the temperature. And of course, that is the temperature in which the water is basically boiling. So water in its liquid state is going to water in its gaseous state. And that's the temperature. So what problems here doesn't. So here's something that we should know or is known or will be given to you. There are a few things here. The heat of vaporization of water. Okay, what is that value? So that value is, let me get it. In kilojoules. Yeah. So the heat of vaporization of water is 2260 joules over 2260 joules over 1 gram of water. This is known. Okay, this is known. So here, what are you going to do? Same thing. You're going to take the grams, convert that to joules, and convert joules to kilojoules. So this is using the heat of vaporization values. Okay, so let's set this up. 25.0 grams of water times 2260 joules over 1 gram of water times. Okay. Joules, we need it in, so 1 kilojoule over 1000 joules. And here you get 25 times 2260 times 1 divided by 1000 times 1. So what do you get here? So if you look at it, you have the grams of water cancel out. Joules and joules cancel. So this is all dimensional analysis, right? And this should give you 56.5 kilojoules of heat. Okay, so this is 56.5 kilojoules of heat. All right, guys. So so what they're saying is water from the liquid to a gaseous state produces that much of the heat. The next is the heating and the cooling curve, and you can leave. So the next is heating. Let's just do it here. So this one was change of state 6. So I can just show it here, the heating and the cooling curve. It's not that hard. Heating and cooling curve. Okay, here's the thing. We express this whole thing in a graph. So here's the amount of heat. No, sorry, here's the amount is the temperature. So degrees Celsius is the temperature. And here's the the amount of heat that is involved in bringing the transformation. And these are these numbers, like some amount of heat, they're like in a graph, like, so the values, some values here, and the units are always given here. There are some units that are given, that that calories or kilojoules or joules, depends. Okay, the temperature, again, degrees Celsius mostly. Okay, so the heat and temperature. So this is the temperature. Okay, now substances, we can show them graphically like this. So here's this. So let's say, for example, this is water, for example. So this is the 0 degrees Celsius, and this is the, let's say this is the 100 degrees Celsius. Okay, so we have this markings on the graph. So from here till here is the 0 degrees Celsius. So the water from 0 degrees Celsius and below, generally 0 degrees Celsius and below, is going to exist as a solid. So this is a solid curve. Okay, it will remain as a solid. After that, the water needs to absorb some amount of heat. Okay, so at that stage, what is happening? This is the stage where melting is occurring. In this melting, the water exists as a solid and also as a liquid. So in other words, the fusion, the melting, and freezing occur at the same, like it's the same amount of heat is being exchanged. So the heat is like, it's stabilized, the temperature stabilizes. So this temperature right here is the freezing temperature. So this is the melting point or the freezing point. Melting point and freezing point. Melt when a liquid melt is when a solid becomes liquid, and freezing is when a liquid becomes solid. You see that? So this is so that's the melting point and the boiling point, exactly the same place. So the amount of heat that is, if the heat is increased, then you are moving from left to right. But if the heat is decreased, then you move right to left. So the heating and the cooling curve shows the exchange of heat is the same, but the directions are different. Okay. Now, after that, after all of the, so let's say this is melting, right? Solid has melted to a liquid. Now, all of the liquid has come after it has absorbed, after the solid has absorbed a certain amount of heat. And how much is that heat? Basically depends what the substance is. It can be water. It will have some value. If it is something else, it will have some value. So this is the amount of heat that is exchanged, the value, the numbers, how much you get by reading the graph here. So this tells you, this is basically the heat of fusion. Okay, that value. Okay, now next is, now we have, this substance has become a liquid. This substance has become a liquid. Now it will remain a liquid. It will always remain a liquid, but it will continue to absorb heat. It will still remain a liquid. It will continue to absorb heat. The water will remain in the liquid state. Nothing much is going to happen, but it will remain in the liquid state. But after some times, when it has absorbed a very specific amount of heat, then it becomes, then it begins to boil. And always, like after boiling, after all it has absorbed a certain amount of heat, then only after that it evaporates. So this stage is the gas state. Okay, this is the gas state, and I'm going to extend this further because, so we will just move this further. So here you have heat. All right, now this temperature where all of the water begins to boil, that temperature. So these are the very critical points in this graph. This is the boiling point. When the water begins to boil. Now water, all of it doesn't boil at the same time. It will continue to absorb heat, but the temperature stabilizes. So what is then this called? This is the heat of This piece right here becomes all this part right here is the heat of fusion. That's the amount of heat. All this heat is needed to convert the liquid to a gaseous state. So now this piece is the heat of vaporization, HVAP, heat of vaporization. Okay, so when all of that heat has been absorbed, only then the water begins to convert to a gas. So meanwhile, it continues to boil. You must have seen when the water is boiling, it forms bubbles. It takes some time for the water to boil. Okay, so this is basically the heating and the cooling curve. This is how it looks. Okay, yeah, so that's the main thing here. Just remember that the heat of fusion, so it's called the delta H of fusion, is less than the heat of vaporization, delta V, the change in heat. It's less because it takes more heat to vaporize substances, less heat to freeze them. So that's what it means by this. Okay, guys? So after this, we studied all that, and that finishes. So you can leave out, because that's like a more complex one, 3.11 and 3.11, because that's more complex, where you're doing combining heat calculation. So this is a bit more complex. Combining heat calculations. Okay, and that finishes this chapter. All right, guys. Any questions so far? Any questions? All good? All right, I'm going to stop recording now, and this finishes this whole chapter on energy. Okay.